Hello guys, my name is William Sjöström and I work part-time at Freemelt developing new melt strategies for new materials and then I'm also a PhD student working with Freemelt machine at the university. So I do a lot of builds for the Freemelt machines, and since my latest publication people have been messaging me on multiple platforms, so LinkedIn and email and so on, asking everything from basic stuff to quite advanced stuff on how to prepare build files. And I would like to save time for me and save time for everyone else. So I'm trying to make a video where I will show you how to make or how to set up where you make your files and how to make build files for the Freemelt. And if you don't know me, I do run my own business. So in the background, you could see some of my printers. We help with design for additive manufacturing and also doing build files. So if you need help and have some budget for this, we can make that happen. I'm also, as I said, a PhD student. So if you go into Mid Sweden University, you can scroll down and find my publications, which are updated all the time. And if you're in the Freemelt machine, I think this one, process development of chemically reduced tungsten, is a quite nice one to check out. Here we do use a Freemelt 1 machine, and we do variation on the dwell times throughout the layers and the current throughout the height in the build, and we also do line melting, and then we have accelerating beams or accelerating line melts as well as different beam speed in each line when we rotate the pattern. And if you want to know how to do this, you can scroll down and in the very bottom here somewhere we have the supplementary materials. So somewhere down here, yeah, here you have a supplementary file. Inside that is all the files we used. So even though it's some of the first files I made for the Freemelt, it can be nice if you're new to the Freemelt to see a bit how you can use the machine. And this session is going to be completely improvised. I'm using a new computer so that I can set up the complete thing that you will need. So in order to make build files, we need to find out a few things. And as I said, this is just improvised, so I could have prepared this, but my idea is that I will do it, save my time and save your time. So you will need something to create your build files in. So I recommend Visual Studio. So that is just like a text editor, we can call it. So we can just go into Google and we can download this for any computer. It's free. Visual Studio Code. So we download this for Windows. And while that is downloading, we can check off the next thing. So once we have this, we will need to install Python. So I think you can go into python.com if you want to and download this. We'll do Google again. Yeah, python.org. Okay. So we need to download the Python installer. And we will, once all these have downloaded, we will install them, of course. So we just accept this, install Visual Studio. So you can see doing everything from the beginning just to also teach you how to set everything up. There is usually one of the most difficult things can be to set it up in a correct way. So once we have not installed these two yet, but we're working on it. Once we have those two, we will also need to have, there is some expansion package or something for Visual Studio. So we need to, inside Visual Studio, find some sort of expansion pack or similar for Python. That will allow you to run your Python file and also to see your packages. So that is kind of the basic. On top of this, we can call it basic Python programming. So we can just have, this is the basic Python thing you need. And then to come into the Freemelt. So what do we need first? Well, we do need a OBP library. So the OBP library is called obplib, I think. obplib, and this is on Git somewhere, some Git, I don't remember which. But we can just, if we take, I think we take this one and we go into Google. So we place obplib Freemelt. You can see here that the library is accessible, and you can see the latest updates and so on. And we will install this through the Python later, as soon as we have installed everything that we need. Okay, so Visual Studio is completed. Yes, and then we need to figure out how to install Python. And I think Python should also have downloaded. So we can run the installer on Python. Launch when ready, yes. And we'll probably run into a few problems that I have not, or that I have forgotten about. Yes. So it's just going through these steps that it gives you. We don't need online help, so I will just leave it at that, I think. Yeah, I think it should be fine now. Okay, so I think actually this one, latest times I've done it, it's actually popped up as a question. Probably you can go into online somewhere to find it. But now we can't create a new Python file, but we can create a text file, and we can probably save this as a Python. So I usually try to save everything inside my user, because that is helpful when you run stuff. Of course, it's not so smart if you do a lot of files, you will fill this folder up. But if just now to try some stuff and just in the first builds you do, it can be smart to have everything in one set folder, so you don't have to set pathless for everything in your files. So now we can just put this as first py. I should be able, I think, to select all files, and then we can just set py as an ending. And I think now it should ask me, yes, okay, so do you want to install the recommended Python extension? And yes, we want to do that. So this is installing now, which will, in our file, you can see at the moment we don't have a play button up here. And also our code would not be recognized as Python if we try to run it, or if we have a Python code here. But once we've done this, I think it will see our Python as give it colors and so on. So it will be easier to make a Python code. Something that I can recommend is to get ChatGPT or something. So some AI that can help you with coding. And now I kind of remember what we need to do, but I don't remember the line of code for it, which is very usual in my case. So now we want to check the Python version to just see if Visual Studio can find it. So if we ask in ChatGPT, we can ask for like, it will give us, yeah, okay, so we can just do this one. And I hope that it will recognize it. Maybe we need to restart Visual Studio. Okay, so it has Python. You can see before we ran the Python installer, this would not come back as anything, I think. So now we need to install the obplib, and I think it is, maybe, I'm not sure if we have the pip now, but we'll try pip install obplib. And if it works, then it's nice, and if it doesn't, then okay, so it doesn't work. And what I usually do when I end up with something like this I recommend to put it in ChatGPT. So I will put like, so next problem, I need to install obplib. And then I will usually put whatever I did here, because then the ChatGPT will know what I've tried, and it will also probably give me the correct line. Yeah, okay, so the problem here was I did not run the pip install through the Python, it seems. So we copy that one and we put this one in here instead. Yeah, okay, so now it's downloading the obplib. And while it's doing that, we can talk about what we need to do once we have the obplib. So let me just think one moment. I think once we have this installed, we will need more, like more packets, we can call it, because you will need to make files. Probably each file will need something like you might need randomized points or something. So then you have like, you might need to install math, but that is usually included in the Python installation. You might have something like random. You might have something to slice files, so it might be something like STL, whatever, handler. But you will find these out later once you make stuff. So we can just say that this will come later. But basically now we should be set to make files, I think. And then we should talk about how does the Freemelt run the builds. So in the Freemelt one, we can, or actually the Freemelt one and the emelt, they are very similar. So we can have like this: how does Freemelt run builds. And then you need to select, choose a build processor. And you do this in the machine interface. I will show you at some point, but now we're just going into the file, so I think we can just take it here, and then I can show you the interface at some other point. But if you're inside the Freemelt interface, you can select one of two build processors. Last year there was only one, and maybe there's another one coming, so this might change in the future. But at the moment, you have something known as BOSS Legacy. And this is the first one that they released, and it was the only one used last year, so this is the one I've been using mostly. Now we also have one that is known as the build directory, and that is the one being a lot of developments around right now. And I would say that the new one is easier if you need to change layer height or more advanced stuff. And it's also easier because all slicing softwares, I can put it like that, all slicing softwares from Freemelt, should have had a text editor here, will use this format. So inside this format, I will put a few dashes here so that we can separate them. So inside this format, we have it controlled by a JSON file. We can say also that it is a zipped format. So it's a bit more complex when it comes to generating files, because each file needs to be inside a zipped folder, and you have to really think about how the paths are controlled and from this JSON file. The good thing is that inside the JSON file, you can do a lot more stuff than inside the BOSS, and you can also, for example, make comments inside the JSON file. So it's easier to see what you're doing, and you have a separate control module in here. But in this case, I will skip this one, because just to make basic builds, I think it's easier. I would say it's easier to use this one to make code for this one. So we should start with the BOSS Legacy. It's very useful when you're doing just, I mean, everything I've done so far in publications has been in BOSS, but we will be moving into build directory soon. But anyways, the BOSS is, instead of JSON, this one is controlled by something known as a YAML file. And inside the YAML file, you have everything like how the machine will access the different files. So I think I will actually pick up a YAML file to show you in a moment. But we should mention in here that each layer or each beam path is an OBP. And this is actually true for the other format as well, like this, but inside zip. So it's inside several zips usually, but and it doesn't have to be named zip, but it's a zipped format. But in this file, we can have the YAML and we can have the OBPs in the same folder. So I think it's quite easy to start to understand how it works. But the thing we need to understand is that we need to have the YAML. This is what we will load into the machine. Load into interface will set path to where the OBP are. Okay, so the OBP is how the beam will behave, and the YAML will set how the build tank will move up and down, how the rake will move, which temperatures we're using, and it will call for these OBPs, which is how the beam will behave within each layer. And I will show you in a moment, because I don't have a file on this computer, but I need to get one. And you will see that we can just put the note that the double dash is equal to new layer, and a single dash is within layer, or maybe just a new file. So I will show you in a moment. I need to fetch the files. I went ahead and I fetched a few files off screen, and inside this folder I put them. So actually inside here I put one folder for boss and one for build directory, just to show you how it can look. So inside the build directory, this is how a build file that you load into the machine can look. And as I said, we will not focus on build directory today, but just to show you how it can look so that we have at least a slight introduction to how it might look. And you will only see this file, which is a zipped format, as you can see. If you unzip it, you can actually open it. And in here you have one file, which is a JSON file. This is the build info file, so this is what controls it. You also have a build processor, which is a Lua file, and we'll not go into it, but it's a bit different compared to what we will see in the boss. And if we want to see this, we can of course use Visual Studio to open them. I usually prefer to go through this not open folder, open file, of course. Because then I don't get a lot of other programs showing up. So we're inside here and we're inside the build directory. And if we want to see this build info, yes, I want to trust this file. So this is the file controlling if you're inside the build directory. And you can see here, for example, you have the start heat, you have the layers, so you have 50 micrometer layers or 500 micrometer layers. Okay, that was quite extreme. Yeah, this is, I don't know where this file came from, but yeah, and then you have basically the OBP files that you will call for. So within layers, you have a jump safe, which is kind of like heating the plate or avoiding smoke, usually called preheat, but can also be called jump safe. And you have the melt files in here. But if we instead look at the other format, which we will be looking at today, we have the boss one. And then what we will load to the printer is this YAML file. So if you check this file, it will actually have the YAML ending. And if we open this file, we can see that it's quite similar, but I think it's easier to go through what happens inside it. That's why we will have this one only today. It's a lot of stuff and a very small screen here. So let's move some stuff. Okay, so inside this YAML file, this is, as I said, let me just check that I'm recording. Yes, I am recording. So I said that this is in the boss way of using the build processor boss. Then you will control the machine via YAML file, and each beam path file is an OBP. Each double dash is a new layer, and each single dash is a new OBP within the layer. So now we have opened the YAML file for one example build. So I just grabbed the build. I hope it's not too secret. And inside this, we have the YAML file, which opens the build, and we have the build files. And you can see here the double dash. So the double dash means that the machine will do a layer feed, and it's basically a new layer. And then you have a few single dashes, which is a new OBP file within this layer. So it's the first layer, second layer, third layer, and so on. And you can see then in this example, we have, when we have loaded a new layer with a double dash, we load this OBP file, which is in some path. Sorry, now we're moving stuff around. This path, oh shit, I don't have a mouse, I only have the mouse pad, so it's a bit tricky here. So this, you can see, is the path inside the Freemelt machine. So if I were to load this YAML file, I have to make sure that inside the Freemelt machine, in this path, so home, Freemelt, desktop, my folder, Wheelco, builds, and this Freemelt build, and this name, and then inside this folder, I need to have this file as well as every other OBP file that I have mentioned in here. If it doesn't, if this folder doesn't contain those files, the machine will not run the build. So one of my most common errors is that I change something or I do a new build, so maybe I want to put it in a new folder, maybe this one changes, and then I forget to change one of these lines inside the code somewhere, and then the machine will not run the build, or it will run some old version of the file. So it's very important to keep track that you're actually using the right path and the right files. But if we look again here, we have a double dash loading the new layer, then we're running this, I call it Wolfram heat circle. And usually nowadays this is a bit, I'm using a mix of my files and files prepared by someone else in this build, so it's a bit chaotic. But usually I try to have under dash and then the watt or the power here, because then we will see it later, but I would recommend to really start doing that. As you can see, this is a mixed file. So if I were to do this right now, I would put double dash or under dash 1500 here just to show that it's 1500 watts. Because then I know more easily how to run this file and how to handle it if I make code to handle it. So for example, I know now that this is a melt file, and it is for layer 1. You can see I have a similar one down here for layer 2. And I know, in fact, that this is a 1500 watt melt, but it would be easier if I had this inside a name, because then I could see that everything was correct. But right now I'm running this heating at the defocus beam in safe locations just to ramp the power up, because when I start the melting I want to have sinter the powder, and I also want to have the correct temperature, and I also want to have the correct power, so the correct emission from the cathode once I start melting. I really don't want to jump into melting a file at the wrong current, because the Freemelt machine uses thermal emission of electrons, so it takes some time to ramp to the next current. So if you switch the current up or switch the current down, you need to have some ramping. So for example, here I have the melt. Before the melt, I have the heating. I don't really care if the heating is not at the correct power. It doesn't matter so much, because anyways, you can see that I'm repeating this heating 2 times even, so it will be sort of a ramp while I do the heating. Then I do the melting, and after this you can see I have a ramp, because the last step in this layer is to do a backscattered electron scan. So I capture an image of the surface of the powder bed or the build or whatever you want to call it. But this is usually done at a very low power. You want to have a power which is safe to scan the beam over the powder bed without having a smoke, and also you want to have a small spot size. So usually you need the quite low power here. I think this one is at 100 watts. So you can imagine that I could not go from 1500 watts up here to 100 watts without having this ramp in between. So this ramp is essentially probably landing the beam inside one of the melted blocks or similar. So one layer is heating, melting, ramping, and then BC scan. And you can see it does the similar thing for each layer here, except it changes the layer file. So if we go down throughout all the layers, in this case I have all the layers in here. You don't have to, I will try to tell you in a moment. But you can see below all these files that we just talked about, we have something known as layers, which is the number of layers the machine will run. So here it is 315. And then if you're observant, you can note that, okay, I have something named 280 here. Why is that? Well, if you're very observant, you would also see that this name is not the same in the top row that we just looked at as it is down here. And this is because I have some support layers and I have some initial layers where I get a stable melt before I move into melting my actual sample, which is 280 layers. So I have then 35 layers, which is support and initial layers, before I start melting my 280 melting layers. But if I were to make a mistake, so maybe I put this at 310 instead of 315, then it would mean that it would only melt up to 5 layers before. So this would be the last layer. It would not make the last 5 layers in that case. So you can see it kind of, this number determines how many times it will go through double dashes. If, to take that example one step further, if I were to put this at 320, and I still only have 315 lines with double dashes, it would mean that it would run all 315, and then it would go all the way up to the top, and it would loop this. So it would do 5 of the first layers on top of the last layers. So in this case, it would mean that I would have support on top of the blocks that I have built. Okay, so make sure that this is correct, or that it doesn't matter if it loops. Another thing to mention is that you could have, if you're only doing, for example, cubes, so you don't have any complex geometry, and you're only rotating the melt a few times, then maybe you only need two double dashes or 4 double dashes or whatever, and you could still have 315 layers because it would just loop. So let's say you only have these lines, you would have like layer 1, layer 2, layer 3, layer 4, layer 5, layer 6, and so on. So it's a way to reduce the amount of OBPs in case your build is not so complicated. So below this, you can see that you have the layer feed things. So this will load when you have a double dash. So when you have a double dash, you will, in this case, go down by 70 micrometers on the build piston, and you will go up the powder piston by 150 micrometers. And usually I will keep the powder piston about the double amount of what the build piston is, just to ensure that I have enough powder. You also have the recoater speed here. I usually go at about 100 millimeters per second. I think the standard one is a bit higher, but a slower one gives nicer raking, but you're also losing more temperature while you're doing it and eating recoater blades in case, such in this case where we have tungsten, the melt area is quite warm, so you will be eating away rake blades if you go too slow. Below this, you have the stuff as post heat, preheat, and start heat. So if we start with the start heat, this is what will run when you start your build, and it will continue running until you reach the timeouts or you reach the target temperature. So usually this is what heats your build platform up to whatever build temperature you have. So tungsten, in this case, I will been running 1230 degrees Celsius. So it means that it will start at whatever temperature the machine is at, usually room temperature, and it will load this OBP, and it will continue repeating it until this temperature is reached, and then it will switch over to loading the first layer. Yeah, and in this specific build, you can see that I actually have the same file for heating the plate and for heating the powder and for post heating the powder. In this case, the post heat repetition is set to 0, so I actually have no post heat here. The preheat, however, I need because I need to sinter the powder to avoid smoke. And a good strategy here is to have something where you have, I would say, at least 20 repetitions of something in this file. Because of course I could make this file so that the repetitions I need is already included inside that file. Then in that case I would have 1 repetition. The problem is if the temperature is slightly too high or slightly too low, I need to change this. And obviously if I change it to 0, then I would just have a smoke because there would be no heating and it would not be good. And if I change it to 2, the temperature would be very high. So by having it at 85, I can fine tune this. So maybe it's a little bit too cold, so I would go to 90 repetitions or something like that. So this can actually be changed while you're doing the build. So a good strategy is to have something that's repeated at least 20 times so that you can go up and down in repetitions. Okay, so this is the YAML file we were talking about. And as we have seen, it calls for OBP files. And as we can also note, I will go back to the top so we can see the path. If you remember, I opened this file from this folder. So this is the folder that I would copy into the Freemelt machine, and I would load this YAML file into the interface or machine interface, and that would tell the machine exactly how to run the build. So you can note that I would, in this case, place this file at the path you can see here, this folder. So 251127 _w iter. I would place like everything, the contents of this folder I would place inside that folder. Because then inside that folder I have the OBP folder, which is here. If I open that one, you can see that I have all the OBPs that I call for here. So this W heat, we could search for that one in here. So it would be we heat Yeah, so you can see I have a few different ones. So in this case, you can see that I have one 1200 watts, one 1500 watts, one 2500 watts, and so on. So that is essentially how the build will work. So in order to make the build, we need to make a YAML file and we need to make OBP files to cover that. So if we want to start, let's say, just to make something simple, let's say that I want to make one cube in one OBP. So we can start with the OBP file. Just to check if the OBP actually works, I would recommend that you try to run something through the OBP library. So you can see this if you go into the Git, and might be a bit complicated, but everything is to read online. But you will find out also commands that you can run through this. So for example, I know that we're inside users print it, and if we go into my users and print it, we don't have any OBP files here, but we can grab one. So let's say something which is relatively okay, so we can grab this one just because I know it's not secret what's inside that file. So if we have this one here, we have the OBP. We cannot open a OBP. However, we can decompile it so that we can open it. So now I need to remember the line, but I think it OBPC decompile, and then we need to put whatever file here so that we can find it. Now remember that we're inside users and print it, and you can see here in the command prompt that we're also inside users and print it. So if you have the file somewhere else, you would have to put the path for the file or switch whatever folder you're working inside. But now we're already here, so we can just put the file name with the file ending. See if this works. It does not. I suspect now that we just installed the OBP library. Wait, did it actually install? Yeah, it's successfully built the OBP lib. So I suspect now that what we need to do is to restart the Visual Studio, because we just installed something and then sometimes it doesn't work the first time. So we'll try to do that. So just restarted it, and we should let the terminal load for a second to give us our line. Come on. Yeah, the line is here. Okay, so let's try to run this again. Okay, so it's not recognized. Maybe I made a mistake. Okay, so just in case it was something with the installation, I tried restarting my computer, but that it did not help. So I went into ChatGPT, and I think I'm pretty sure I was already from the beginning. But the problem is that this OBPC cannot be located, so we need to change the path for that somehow, and I don't remember how. So I got this guide from ChatGPT, so I will just go through it and see if it works. So first we need in the command prompt, see if we can run this command to get where the scripts are located, and it gives me this line. So we should copy this line, I assume. And now check, yeah, okay, so now we should have this one. We put it in here, and then we need the output. See if this can be put in here. And we run it. It is incorrect. Let's see. Okay, so we will give this to ChatGPT and see why that happens. Okay, so that was an easy fix. We should not have the brackets in there. Happen. Yeah, we pasted that. Okay, so there we have the obpc.exe, which was added today. And then what do we do next? Yeah, but we know it is. Okay, but we can we run it in here? I think so. Yeah, we know OBP is existing. If it does exist, which it does, run it directly. What does this do then? Okay, so it runs the help. That we can do. See what happens. Yeah, and this is the OBP-C that we want to find. It can basically, we want to decompile and compile files at the moment, but we cannot call it from our command prompt in Visual Studio, and that's what we need to figure out. And this line, oh, this actually decompiles what we want to decompile. That's not what we want to do. We want to fix this. Why does it need the output? We will run this and see what happens. Okay, so this is what we ran, and yeah, it does show the OBP viewer as well. We will come into that later, but for now we'll give this back to ChatGPT and see what we do to fix this. Okay, so we need to add something to the scripts folder. We should add this one inside the environmental variables. So we can go into environmental variables. This controls where we can run stuff from. So for example, you can see the path here should contain everything. So I think what ChatGPT is telling us is, oh, we should not have that one there. We can put this one like that, and okay. Yeah, and we have done a new one. So we have put that one in. And then, this command will tell us where the OBP-C is, I think. So if we run this, it shows in here where we want to run it. So maybe, if we're lucky, we can run this now. No, we cannot. Okay, it's still something wrong. What? Oh, we did not restart the terminal. So we try to restarting Visual Studio. Let it load. Yeah, now it worked. Finally, okay, so if you run into that problem where it cannot be found, you need to do what we just did, find out where the OBP-C is located, and then go into here, look for environmental variables, go in to environmental variables, find the path, edit it, and put the location for your scripts in there so that we can run it. Okay. So now we have actually run this. You can see that successfully decompiled this file. And when it decompiles it into OBPG. And OBPG is a format that we can open. So if we now go into our folder or path, change it, and when we go to the last one, you can see that we had this one, and now at this time we created a new one. So we will go ahead and we will open this file. And this one we can read. So inside any OBP file, this is what you will kind of see depending on what you have done. We will come into this, but this specific file, you can see it opens a OBP, and then we have time points, which is basically spot melting. You have points, which are coordinates, you can see here. So this is 1 point and the next point, and then it goes through, so it will melt them in first point, second point, third point, and so on. So if you want random points when you make this file, you would shuffle them, for example. And in these time points, you will, for all the points which are contained within points, you will define the same spot size and the same beam power. So if you need to change this, you would then define more time points, basically. So if we want to look on this, how this file looks instead, so now we can read it. We can read the OBPJ, but we cannot read the OBP. However, we can view it because there's a viewer included. So if we go OBP viewer, and we put this exact name that we had here, This will run the viewer, which will open this file, and it will show us everything that happens inside that file. And it seems like we have not installed matplotlib. So that is something that we need to make plots, and it's used within this OBP viewer. So we need to run that, and I think we can Python 3. Yeah, it should be possible, I think. So we run this, and it should install matplotlib. So that is what I meant before, that you will come across packages that you will need to make certain things or show certain things, and you will need to install it. Matplotlib is used a lot, so it's nice to install this one. Okay, successfully installed. So now, since we have that one, we can, if we go just the arrow up or the arrow pointing upwards, we can do all the things that we have recently done. We don't want to install the matplotlib again, but we do, however, want to try running the OBP viewer. So we'll do that. And you can see now that since we installed the matplot whatever lib, you can now open this OBP viewer. And this viewer is very helpful to show one OBP file. And you can see the window scales however you like it. So in reality, you should follow this scales as it's normally square, but it can become confusing if it's not. So there's a few things you need to see in here. You have this scale, which is the speed if you have a line. Now we have time point, so it's spot melting, so it will not be very useful. However, we will see the beam power and the spot size for the latest spot. So since it's only one time points in here, we will have the same throughout all. The next thing you will see here is one value here and one value here and one value here. So 76 is the number you're on, or the step inside OBP that you're currently on. So currently you're on 0.76 and you're showing 100 points. So if we were to put this at 10, you would only show points from 66 to 76. So if you want to show only the last one, you could go to, if we put 2, we have the latest 2 points. Okay, so if we want to go through all of them, we can go like this, but you can see we can only see the 2 latest one for each step. So maybe we put this at a quite high value, then we'll see all of them. So when we go from the start, you see how it starts filling points and where it hits and what area it hits. And if you remember, this is the heating in a circle at 1200 watts. So it will just be quite there's a lot of space in between the spots, and the spots are very big at 1380 micrometers, and the beam power is 1200 watts. And that is basically it. And you can see the same thing. If you go in here, we have the spot size and we have the beam power, and we have all the coordinates that we're using. And this specific thing, T, is the dwell time for each spot. So you can actually change the dwell time for each spot. And if you want to see what you can do and what you can't do, I think we can do like this. We did our first Python. So now we can do import, because we want to import OBP lib. And I usually put this as OBP, just to not have to write OBP lib every time. And we can go into these definitions. So if we go into the definition, you can see what's contained within OBP lib. And you can see here that OBP lib contains a number of things. So now in the most recent example, we were looking at time points. So we can also look at the definition of time points. If we go to this definition, you can see here that it contains points, dwell times, and beam parameters. So remember, we have points is just x and y. We'll come into that. We have dwell time, and you have beam parameters, which are these two. So if we look here in the definition of OBP lib, you can see that here you have the beam parameters. So if we go to this definition, you will see that it contains spot size and power. So it is exactly what we had up here. So that is why the time points imports it as a beam parameter instead of having the spot size and power separate. If we want to do a line, we can go into this line instead. So that's just melting a line. We go into that definition, and it's quite easy. But then you can kind of come back here and understand what you need to do to make each beam path that you need to do. Because here, for example, you can see that we have 4 inputs, and the self, of course, but that's just calling back to the self variables inside this class, that's line. But you can see we have 4 inputs, basically. And you can see also the comments on what these are. So P1 is a point, the starting point of a line. P2 is another point, the end point of a line. The line is always from one point to another point. And then, of course, in this case, you have also speed that you want to go from point P1 to point P2. And you will do this with some beam parameters. Remember beam parameters, we can, if we don't remember, go back into the definition, look for beam parameters, look for their definition, and we can see that that's spot size and power. So that makes sense. And if we want to do something else, so remember I said I was doing accelerating lines. That is quite difficult to do in some other systems because then you would have to segment a short line with some beam speed and then do another line with another beam speed. But here it's actually quite simple because you have the accelerating line. So if you go into this definition, you can see that it's quite similar to a line. So you remember the class line, which would do a line. Here you have the accelerating line. So you have P1 starting point, such as you can see here. You have P2, the endpoint. And then since we're doing acceleration, we also need now the it seems like the the definition is a bit yeah, it's not so logical here, but you can see SI is basically V0, so it is the initial speed, and then you have the final speed. So you'd have initial speed and final speed, and you would have the beam parameters, which was spot size and beam power. So whatever you do, you need to define these sort of things. So now we can come into, if we think that we want to melt just a basic cube, we can make this in our first file. So what we need to do in the end, we need a OBP. So if we come back and we check the definition, you can see that we also have the file handler, and inside the file handler we have the write OBP, and that one we will need. I haven't looked in this definition for a very long time, so it's yeah, I basically haven't looked at it, so I don't really know what we will see here, but we should have something that writes an OBP, so this definition. And that needs some OBP data, which will be written, and it will need a file name. So we can have this, because that is, in the end, we want to make a OBP that we can run with this script. Oh, didn't we copy it? Let's see. Okay, so in the end, this is what we need to do before we close the script. And if we want to make lines, then we should use this line, meaning that we need to have the inputs which we had here. So if we copy these inputs for line, so we'll have some line, or rather we would have OBP dot line, because remember we're importing obplib as OBP, so we can have OBP line, and then we would have the stuff we copied. So this is the inputs we will need, and this also has the beam parameters. So we will need to check out the beam parameters. We will go into the definition here, and that has spot time and power. So we will also do OBP dot beam parameters, and we will, in that case, need the ones I copied here. So spot size and beam power, meaning that imagine that we're doing a cube. We will, in this case, just consider a very simple cube. We'll do lines like from left to right and from bottom to top, we can say. So of course we need dimensions, so we can call it cube side, or side, and maybe we want this to be 10 millimeters. And in this obplib, everything is input as micrometers, so we can put this micrometers, so it is equal to 10 millimeters. If we have a cube side, that is. Maybe we should make it a bit bigger to make it easier to see. Make it 15 millimeters. That is something we need in order to make our lines. We also need to know how many lines we need. So we need some line offset. So really, to make a file, you just need to think about first what you need to define your lines, and then what you need to satisfy the line or the time points or whatever you're doing, and then how to get to the right OBP in the end. So if we do line offset of maybe like 300 micrometers, so I put here just 300 micrometers. You can put 15. Oops, 15 we said. Okay. So then, how many lines will we have? Well, we will have number of lines. And this has to be, it cannot be a decimal value because we cannot have half a line. That's not possible. So I will make it an integer, and then we need to have the cube side, which is the complete. The copying in this computer is weird. Like this, and of course we will divide it with the line offset. That will give us the number of lines within one cube. Then in some cases you need to think about if these are not, I will not care here, but if these are not equally dividable, you might find that you're not making exactly the dimensions that you intend to make. And anyways, the spot size will probably be, or for sure, it will be outside of your cube side. So if you aim to really make a cube that has very good dimensions, you have to know first a lot about your process, and then you have to think about how do you actually melt it, because it will be, at the moment we will melt the first line on the edge of the cube, and the last line might not exactly line up with the end of the cube. But anyways, here we have the cube that we need to melt, and we want to melt this with whatever we have here. So P1 is, we can have start, actually these will be different for each line in our cube, because the coordinate, the start coordinate for the first line throughout the cube will not be the same as the top line, for example. So we can have instead the start coordinate. I can put it just to be sure. We will have start coordinate of cube, and we can actually have even an x and a y, just to make it really clear. So we will have the same, but for y. So this will put it in the center, 0, 0. And this means that we will need to run a loop from over the number of lines, basically. We can call it some variable I, for I in range of this number of lines. So for each line, we will need a start and end coordinate. Yeah, so if we have a cube, we can imagine that we have a left coordinate, and we will have a right coordinate, and this is for each line within the cube. So the left coordinate, if we think about it, we need to have it a point, because it's going into, actually we can have, oops, yeah, we should have that one in there. Yeah, I'll leave this at the moment here. But the first one will be, if we just imagine like x and y, what will the x and what will the y of our first coordinate be? And we can say that the x of the first coordinate will be this one, and the y will be this one for the first layer. But we also need to put for each new layer. So each time this I goes for the next number of lines, so plus I times whatever line offset we have. And the same thing does not apply here, because the left coordinate will always be, yeah, sorry, actually we should have, it's not the x that is changing, it's actually the y if we're doing from left to right, from bottom to top. So we'll think about the next one. Yeah, so it's actually the y coordinate that will change for each line in our cube. So we will do the same for the right coordinate, meaning that we need some x and some y. And here the x will of course be the start plus whatever our cube side is. And our y has to be the same since it's a flat line. Otherwise we would start making diagonal lines, which we don't want here. So this is the coordinates we need. But in order to make this line, remember that we need the beam parameters. So we need to, no, sorry, the beam, we need the point. And actually, I can see that I've slightly messed up, but if you go into this definition of the obplib, you have also point here. And if we go into this point, it is very easy to see that we have x and y. So actually, I will copy this. We need to make a obp.point of x and y. So we'll put here obp.point because we want to make this a point. Oops. And then, of course, we have our x and our y. So we need to do the same down here. Let's see. Okay, so we're defining a point, and then we have our P1 and our P2, so we can go ahead and put our left coordinate is the same as our start position. We're going left to right. If we want to go right to left, we could just reverse these two. So if you think about that, this is just doing everything outside of a class. If we want to make a class, such as in all the cases we've seen inside the library here, where everything is in classes, where we can call for the class instead of making this every time, then we would just have some function for each side, and we could call for, we would make the change inside the class so that if we want to have from right to left, we would just reverse these two. We need some speed, some beam speed, and we need some beam parameters. And you can see here that the beam parameters, we can call them BP. We're already defining them, but we are missing the inputs here. I can't copy in this computer. Let's try again. We need to define these. So for spot size, maybe we can go 300 micrometers. And for the power, maybe we should go like 900 watts or something like that. Should work for some materials. And you can see that we're still missing the speed. So we need to also define the speed. And the beam speed, I will just put something like 100 meters. 100,000 micrometers per second. So this is same as 100 millimeters per second. So a quite slow process, but should be possible to do some of the difficult to melt steels and so on in that range of parameters, I think. And of course, this is something you need to try out for your materials, either check publications or do some experiments where you have one cube with each setting, or copy our approach with doing gradient development, and you will have some idea of what to have here to get solid materials. Okay, so what we still haven't done is writing this to the OBP. So we need to call for the OBP because we're doing a OBP, and write OBP. Remember, we found this inside the file handler. So if you go into the file handler, you can see how to define this, but we've already copied. We need OBP data, and we need some file name. So we can make this. This is our first OBP. And remember, it is a good idea to put the power here. So I put 900, and it's a OBP. Don't remember to put this ending, because if you don't put this ending, it will not become a OBP when we write the OBP. And here we need to have something holding everything within this loop. Remember, this is just one layer that we're doing right now. But still we need to hold this, because now we're making a loop and we're making a line, but we're never saving this line throughout this loop. So we need to put, let's say that we can have a melt holder. So this will just hold our melt lines. And we need to define something up here. Oh shit, I can't sorry, I can't copy stuff with this computer because they switched the keyboard stuff around. Okay, so a melt holder, and we will just have it as a, I don't know what it's called, but kind of an empty array or something like that. So within this loop, we could put stuff into this, and then you have either append or extend. So we can either append or extend into this. I can call it array, but I'm not sure if it's called array in Python or not. Yeah, so then we need to put stuff in here from this line. So if we think about how to do this, we should have something we want to append, or I think we want to extend in this case. But we can take this one and we'll extend. So we'll add on top, and the extend should have a bracket or parenthesis. So this we will extend with this line. So each time this loop goes around, it will extend this array with whatever is in here. So the first, it will take these values and put here, and it will make one element for each each time the loop runs. So I might have missed something now, but we can try running this and see if it works. So since we have the Python extension thing installed, we have the run button up here now. So I'll just go ahead and press that one and see what the terminal says. Okay, so it says something here, which is not working. So line object is not an iterable. We're having a problem here in line 22, where melt holder extend. What if we just put a pen there? Maybe we should have. Will that work? Yeah, okay, so append worked. It might be a good idea to put some output here, like, okay, so after this we could have OBP written or something like that, or OBP failed if we failed it. Yeah, but now if we go into my users and print it, you can see that we have actually written this first file, which is our OBP file. Since we have that file, we can copy the name of it, and we can go back into, here, and we can run OBP viewer, and we can have that name .obp, run it, and then you can see this is what we created. So maybe we can use the zoom thing and just look here. So for this file, we go, the star is where the line ends, so we go from left to right and from bottom to top. So you can see that we have this offset, and since we have here a line, you can see that we have the color is red, so we are at 100 millimeters per second, and we have a beam power 900 and a spot size of 300, and we do it like this. Okay, so that works. And then one thing to remember is that before you can run anything else, you can see now we can't run anything here because we have the OBP viewer open. So either you need to go to the cross, or I think you can also press Ctrl+C and you have a keyboard interrupt, and then you can run something new. So if we just to remember how we can handle these files, in case we run the process now and we realize that, oh no, 900 watts is too much, we have to change this. We cannot change. I mean, we could run, if we have this script on the Freemelt computer, we could just run it and replace this OBP with something else. So we'd just go in here and we would replace this 900 to maybe 800 or whatever, and run the script, and it would make a new file. But usually, at least in my case, I make the files in one computer and then I run the Freemelt completely separate. So then you would be stuck in the Freemelt, you would have this file and you can't really make any changes, except you can. The thing you would do is, like we did it before, you would go and write OBP-C in the terminal, in the Freemelt instead, and you would run the compile, and you would take whatever name you have here, and you would put it there, OBP, run it. So now we have created this OBPJ, which is readable. So we can open that one. And here you can see what we have inside this OBP. So this is what we tell the beam to do. You can see that we run OBP line. We have the spot size and beam power. For the line, since we only have one, I mean, now I did the file, so now I know that we only have one line in here. If you didn't make the file, or if you made several files, or maybe you have time points and so on in here, maybe you need to change several positions of this. Then you can use Ctrl+F, I think, and you can do like find and replace. So now, if we want to change the beam power, it might be a good idea to just check how many you have. So actually, there is one per line. So if we want to change from beam power 900 to something else, we can just put it in here, and we can replace this by maybe 800 and replace all. So you can see now we have 800 here. We will save it. Now it might become a bit confusing if you're not keeping track of this, because remember, we still have the file name 900 here, but now we have 800 watts inside it. And before we can use this, we need to compile it into OBP again. But first, I just wanted to show you that you can see here if it makes sense or not. Now we've already looked at the OBP viewer, so we know that it makes sense. But you have here, for each line, the positions. So for example, the Y1, 0, Y2, 300. And remember that we put a 300 inline offset. Maybe it's a bit confusing that we also put 300 as spot size, but it's not the same thing. You also have the spot size as 300 in here. We could actually change that as well, just to show you what we're doing here. So we can search for spot size, and we can replace it by spot size. Maybe we want to do 200 instead. So we save this. And now we still need to compile this, because if we do remember we can run the viewer, this file, and you know this is obpj, but we need to run the obp because that's what the machine will read. If we read this, we will still have 900 and 300 here, but if we first go obpc compile, and then we need to get, sorry, not that one, we will grab this one, obpj. So now we're, instead of decompiling it, we're compiling it back to obp, yeah, normal obp. So okay, so now it asks, do we want to overwrite it? Yes, we do. And then we can go back and we can run the obp viewer. And remember now that's confusing because we had the 900 in here because that's our original file. But in case we wanted to change something during the process, and we changed it here, this. So now you can see that actually we have 800 and 200 in here, just as we did the changes. So that is one way you can change the file while you're doing it. Now, just to get back to what we had, I will run this original script, and that will replace the file we had. So if we run this viewer again, we will be back to 900 and 300 in the beam power and spot size. So the settings themselves for the parameters is very easy to change there. The coordinates is maybe not as easy to change that way. So the next thing we need to do to get the machine running this is to make a YAML file. And of course, the YAML format is quite easy. So in this case, I would suggest that we just do it manually. I have a script for generating these files, and you can do one too. It's very easy, but it's the same format. So let's just grab the one I had here, because they will look exactly the same. You can grab any one you have in the machine from a demo build or whatever. And if you don't have one, I guess you can message me, and I will do like this. So instead of scrolling through all of them, I will put my marker here and I will go up, and we will remove everything but one layer. We will say that we can run one layer. And now we only made one OBP. So actually we can decide where we want to put this. Maybe I want to put this at my first build. Oops. So my first build in the Freemelt machine. Yeah, and I just put it in OBP. So I will go to my desktop, I will make my folder, and I will make this folder my first build. And that is where I will place this YAML file. So note now that from this, we cannot comment inside the YAML, unfortunately, but this is the path inside your Freemelt machine where you need to place the YAML that we're currently making. You also need to put your OBP name here. So we could just have this OBP that we made. Oops. Your first OBP. And you're making one layer is fine. We will save this as. We will go to, oops, I think I pressed the wrong one. This is a web folder, which I shouldn't have pressed. Yeah, so let's go here instead. So this is the first YAML. So let's say that we want to run 50 micrometer layers instead. Maybe we should switch this. And the speed for the rake is fine. So now I could go ahead and put this in a machine, and it would not run. And then we need to think about why would it not run. It is because in this file is fine. We have that one, and we can make sure that it's inside the OBP folder. Then it would run from that sense. But we also call for this file, which we do not have. So we need to make that one. So let's say that we want to make a spot heating pattern. And then we need to think about how can we make a spot pattern. So we go and make a new file. We make a Python file. And just to keep things on track here, we can put this is my first spot heater slash jump safe. So Freemelt calls the preheater, they call jump safe for some reason. Because it's it's safe to jump, or a file that is safe to jump, I guess. But anyways, here we need also to import obp lib as obp maybe, and then we need to check what we had in here. We go to the definition. Here we want to make a point. Remember that a point is just a coordinate. So actually we want to make a timed point because we want to have a spot heater that is having a dwell time or staying at the position for some time. So if we go to this definition, you can see that to make time points, we will need this. Let's see. Yeah, we have done our YAML. We'll put it here. This one we don't need. We don't need the time points anymore. And this is my first preheater. So we need to make obp dot timed points, and we need to have these inputs. We can go into our first. We remember that we need our points. And we need our beam parameters. So I'll just go into our first file because here we already used the points. So we can grab this format, but we will not use the same coordinates because now we're using points. So maybe we're using X and Y. We will need a lot of these points because we're doing a pattern of jumping points for heating. We will also need the beam parameters. So I can go ahead and copy this line because we will need to make beam parameters. And now we're doing a heater. So remember that we will need everything we did in here. We will need at least the cube side. We can keep everything. I will just bring this. And I will bring also this because we will need everything in here, I think, except maybe the beam speed. So now we just copied what we had, the cube side. So now I can call it instead heater cube side. And probably we want to have a bigger area heated. So maybe we have this at 40 millimeters. Remember that we put some comments here. So just to make it less confusing, I will change those as well. Now we could have a line offset between each line of spots, but I would, I mean, if we just, there's a lot of ways to generate points. But if you're doing a simple like cubic distribution of points, we could have just a spot offset maybe. And I have the feeling that for a heater, we should have this at like 1 millimeter maybe. And to make sense with the line above, we will put the under dash there. Number of lines we will not have. However, if we're having a cubic heating pattern, just because it's easy to imagine and easy to make, we will have number of points instead. And the number of points, of course, should just be number of points per side. So we can have this one over the spot offset. And we can actually have number of points per line, I would call it. Yeah, or per spot line. We need the starting coordinate, and of course, if we have our cube at 0, 0, maybe we want to offset the heating pattern. So now to make it more simple, maybe we can make it, instead we make it 30 millimeters, because then we can just offset it by 15, and I think it should be relatively centered over the cube. Okay, and the spot size for a heater should probably be around 1500 micrometers. The power should, I mean, just to keep it simple, we'll keep it at 900. The speed we don't need because it doesn't have a speed, so we'll replace this by dwell time for the heater. Maybe 100,000. I think this is nanoseconds. I need to double check that, but we can have it 100,000 for now. Okay, so we need to make our coordinates for this. So we should keep track, similar to what we did in the line melt. We need some holder. So maybe we can have points holder. And we can have this just empty for now. So remember, we can extend or append points into it. And I think we need to loop over the x coordinates and the y coordinates to get them. So we could have for I in the range of something that will be like the number of points, and we already did this one here, number of points per line. So since we're doing a square, this will be both in x and y. Of course, we could do a circle or whatever we like, but I think keeping it square now, just for simplicity, is a nice thing. Okay, so then we need to think about what do we need to do here. We need to find some x coordinates, and this needs to be where we start, and then we need to add the distance between points. And we have spot offset and we have a start position. So let's put the start x, start of cube x, and then we need to, for each I, that we loop, for each number of points that we loop, we want to step this up by the spot offset, so that we move from point to point to get the coordinate. So for loop number 0, this will just be the start coordinate 0, and then for loop number 1, it will be the spot offset, and then for loop number 2, it will be 2 spot offsets, and so on. And that should actually be everything we need for the x for the moment. But inside this loop, we also need to loop over the y, because for each, if we're doing a cubic distribution of points, we need to also have the y coordinates for each x coordinate. So we can do for something, let's say n, in the range, and it will be, since we have the same condition or same dimensions, we can use the same size here. But actually here we're looking at the y and not at the x. But since we have a square, we can have the same thing here. And then we need, of course, to find the y coordinates. So we'll put y is equal to something, and then of course we will have the start. So here we're just finding the coordinates, and we need to do exactly the same thing, because we need to add one spot for each offset here, like this. And when we're inside the inner loop, so for y coordinates, then we know the x for that coordinate and we know the y. So then we can actually define the point that we have and get it into the holder. So the point or the coordinate or whatever we want to call it, so let's call it just point. I will make a big P, universal P here. So the point, we can just have, I think we had it here already, OBP point will be here. And we need our x, which was a versal x and the versal y. So then we define our point for each coordinate, but we also need to put it into this points holder. So remember, exactly like we did before, we will have here append it, and we will append this point. So actually, if we were doing like the last one, we could have had, we could actually do like this and say one line. I think it makes it more readable. So here we're just appending this point to the point holder. And what do we need to do next? So we still need to define, or sorry, we still need to have the dwell times. And actually the dwell times, if we assume that we have the same dwell time for each point in this heater, we will just need a dwell time holder that is the same length or the same number of elements as our points holder. So we can put dwell times list, and we can have this as we already had our dwell time defined here. So we'll just have this dwell time, but we will have it repeated. And the way to do this is we can just have the length of the points holder, because we need them to be the same length, so that we have one dwell time for each point. And then, just for now, we could keep it like this. And we need to define the time points still, because now we only have made points inside the points holder. So to actually make the points, we will need this beam parameters. I will move it to the top because I think it's easier if we define everything in the top. And we already had a spot size 1500 and a power of 900. And the points we have defined, so we can remove that one. So what we have left, we need to define the time points, and then we also need this bottom line here, which is writing the OBP. So I will copy that from the last script, that was lines. Here we will not, this we need to change because we will not have the melt holder in there. We will instead want our points. But now we need to make the time points. So let's say that we define the timed points as we need OBP dot timed points. Maybe it's not great to have the same here, so maybe we can put it time points heater. Actually, we should have probably, maybe it's better to have it like this. Heater time points. And inside the time points, we already put it here. Okay, so we don't need the lower line anymore. We need our points, which we have saved inside this point holder. So we put that points holder there, and then we need our dwell times, which we made in dwell time list. So now hopefully the points holder should be the same length as dwell time list, and then we have beam parameters. And what we need to do next is to write this file, as we said. So now we need to write this as a list because we have a list of this is a list because we have several points in here. So I will put it in a bracket. Okay, and then we need some name. We have it still at 900 watts, but we should probably have it called like first heater. We should have put the other one. We'll call it first heater. The other one should probably have been like first melt or something. Okay, so now we need to save this as well. I will call it my first heater generator. And I think now that maybe we have something. As I said before, it might be a good idea to, I mean, this is quite easy. We might fail at some point, but when you start to get into like several thousand lines of code, it's a good idea to put a few like prints, and we could have like, okay, so if we pass this line, we have OBP has been generated. So then we could have, for example, I mean, if we're looking for errors, we could take this line in here and we could have like, okay, so maybe coordinate number I has been generated, blah, blah, blah. And at some point, maybe we fail or something, and then we can find this error. But for now, we can put this here and we can run it. So we can see that it ran fine. It created this OBP. So if we now look at this OBP viewer, and we put the name here and we get it up. Okay, so now we should see what we have. Oops, let me get this a little bit smaller so we can have it. So what's happening is that we're stepping here, Yeah, and you can see here that this is not what we wanted to do. So we're actually getting out of the X loop too quickly. We're only doing one coordinate for each Y. And we don't want to, I mean, we want to do all of them. So why is that happening? Probably something with a range here. So we're doing this for the n range of, okay, so we have the I, yeah, we should have an n here. So if we run it again, yeah, we need to, now I was trying to run it with this open, so close that one and we run it again. I think it already ran in the background, but run it, yeah. And then we can get this OBP viewer again. And now since we're also going over the n, now we get all the points. Okay, so you can see that we're going yeah, we're going through the points, and if we put this at some really high value, we'll see all the points. And this is a heater that might work. The problem is that with a heater, you normally want to avoid smoke, so it's maybe not a good idea to land one point after another. So we can see that now we start at the first point, and then we go to the second one, and so on. So normally, probably you would like to have an ordered pattern where you jump a certain number of points or something like that. Just to make this simple, we could shuffle the points just to show you how to, an easy workaround if you need to make a file quick or something. So then at this point we have our points. So what we need to do here is we can have random, and I think random is not included in the standard Python. So then we need to, you can see it's not recognized, it's currently white. So we'll go up here and we'll put import random, and then we will recognize this as a random function or class. I'm not sure what the name is in Python, but it will recognize it so we can run it. And then we need to shuffle this one. So we should take that name random and we'll do a shuffle. If you want to know what you can do within random, same thing, you can go into random and you can go to the definition. But now I just know that we can do a shuffle. So I'll save it and we can run it. Now we have this one open, so I have to close it. See if it runs. Yeah, okay, so now it should have shuffled it. So if we open the viewer again, the points should, if everything worked, be shuffled instead so that they are randomized. And this might not be the best either because you might risk having them landing one on top of another or one before the after, that they're too close. So maybe it's better to do an ordered pattern. But this should, randomly it should be close to working. I've done many successful builds with random pattern and it usually works. Yeah, so you can see now we're randomly heating this pattern. So now what we can do is we can put this one inside our heater because we already have it, right? Control C. We put this in here. That file we have. And now notice this pass is probably not what we want it to be. So maybe we can just grab this one that we already changed to our first build. Like this, but without that OBP. And like that. Okay, so now, yeah, now this should be fine because now we have the only two OBPs that we're calling for. We have here. We have our melting OBP and we have our heater OBP. So this is how to make your first basic build. You would just make sure that you follow this sort of path. So if we go into my my folder here, we need this first heater and we need our first OBP. So we would take these two, maybe copy them. We would make new. We can call it first build. Actually, I think we called it, yeah, first build. And then inside here, we would put a OBP folder. Inside the OBP folder, remember that we'll put this one, first OBP and first heater. That's the two ones we need. And we also need our YAML file, which we did it manually here. So we can just grab that one from here. First build YAML. So we'll just put that one in here. And then if you copy this complete folder and you go to your Freemelt and you put it inside here and you load this file into the build area of your interface, then you should be able to run this build. So the build should work as it is. Yeah, so next step I will do a more complicated build and maybe load it into the machine as well. But let me know if you need something specific and I will try to steer it that direction. But I have one build in thought that I will make first. So thank you for listening so far and hope you learned something.